from Mudanya University in Turkey, and he's going to tell us about weekend axioms, idempotent splittings, and the structure of learning, from algebra to artificial intellect. So let's welcome, please.
Thank you. So first, I would like to begin by thanking people. First, I would like to thank those who made this work possible. The list starts with my thesis advisor, İlhan İkeda, Professor Lou Kaufman, Professor Necmi Gürsakal, who is interested in AI and writes on machine learning, Yılmaz Kılıçarslan, who also is interested in machine learning, Rüştü Murat Demirer, who is in the audience and is also interested in machine learning, and Yağmur Denizhan and Alexander Borovic. I also would like to thank Boğaziçi University, Mudanya University, and Feza Gürsey Institute. And I also would like to thank Vasily Manturov and Seng-Jong Kim for organizing these seminars and inviting me to give a talk here. And I also would like to thank people who influenced me and guided me along my path of exploration in science and mathematics. That, of course, the list is actually much longer than this, but I wanted to mention my high school teachers, Tom Pearson, Klaus Kaduret, Selim Tezel, mathematics professors, Robert Gunning, John Conway, Ingrid Dobeschis.
Did you meet John Conway in person?
Yes, I did.
Oh, it's great, yeah. Really great that you met Conway in person.
He inspired me a lot, I should say. He was interested in, at the time he was co-authoring a book on lattice or classification of lattices and lattice groups with another person.
With Sloan, Conway Sloan?
Not Sloan. I never met Sloan, but I heard a lot about him.
You know, nowadays we have a project called Reading Books Together. And actually, I'm reading several books with Conway, for example, Conway Sloan or Conway Smith, about different topics in lattices, combinatorics. And I'm happy to share my joy of reading great masters. Okay, please.
That's great. That's wonderful. Thanks for sharing this. And then Professor Ingrid Dobeschis, who pioneered the wavelets, the theory of wavelets. Professor İlhan Aksay, who is in chemical engineering and is interested in biomimetics as well. And Professor Zoltan Szabo, Professor Alp Eden, Professor Ercüment Ortaçgil, Professor Ahmet Feyzioğlu, Professor Stephen Voss, who is a philosopher, and Professor Şahin Koçak. And I also would like to thank my Master of Science thesis advisor, Ferit Öztürk. I also want to thank anyone who influenced, supported, or guided me in any way in my journey, including my family. So I want to begin with the question, where does mathematics begin? Or how does mathematics begin? In the figure, we see the famous Rubin vase, which if we focus on the white part, if we see the object as the white part and the background as the black, appears as a vase. But if we see the black as the actual object and white as the background, then this appears as two faces looking at each other. And in either case, we distinguish in this picture between the white and the black region. So the primal act is telling things apart. And then we need to distinguish between what is the figure versus what is ground. And this resembles what is in signal processing, distinguishing between a signal and a noise. And this is not simply a metaphor, it is actually the structure of perception. And I would like to mention Merleau-Ponty and phenomenology at this point. Our brain itself, situated in this world, it works as a splitting machine that distinguishes between objects and tells things apart. And before any question, there is this: our consciousness is not a blank state. It's an organizer. It highlights this and lets that fade. And this is the biological and phenomenological root of everything that we will discuss. And the act of separating figure from ground is not just a perceptual curiosity. It has been formalized as the very foundation of logic and form. In
Excuse
1969,
me, I would be
yes.
very happy, and this is my a long dream of invariants in pictures, whether we can locate a picture as an invariant of object. So, if we have a picture somewhere in topology, can we separate it as an object, as an invariant? So maybe local combination. I would be very happy if it could be useful in artificial intellect or elsewhere.
I think, well, the talk will hopefully reach that point. I also share the same hope. And I think that invariant theory is very, very close to the topics that I'm discussing in this talk. Yeah, thanks for pointing that out. And Lou Kaufman talks a lot about George Spencer Brown and the work Laws of Form. And the first law is in that book, Laws of Form, is drawing a distinction. From this single operation of marking a boundary arises all of mathematics, logic, and structure. And in actuality, in the real world, the cell membrane in biology, the focus of attention in cognition, and the idempotent splitter in algebra are all embodiments of the same archetypal act. And this is sort of a diagram to illustrate it. The mark could be the circle, which is the boundary of a disk, and the circle separates the plane into an inside and outside region. And the circle creates the form. And drawing a distinction, the primal act is creating a boundary and separating inside marked state and outside unmarked state. And this is not symbolic, it is operational. And all logic, mathematics, and form arise from recursive distinctions. Re-entry of distinctions lead to self-reference and complexity. The cell membrane, figure versus ground, idempotent splitters are all instances of this. And here I would like to mention the similar to the notion of an invariant, or the, after, for example, the analog of it in number theory could be seen, for example, if we focus on multiplication on the set of integers, well, the ultimate splitting, the ultimate building blocks of multiplication structure on the integers is primes. And these are the sort of in some, it's analogous to invariance, maybe in topology too. And in philosophy, there is the notion of distinction as arche, the first principle. Distinction as the primal operation by Spencer Brown. In biology, cell membrane, life versus non-life boundary. And in cognition, figure versus ground, perceptual splitting. And in algebra, idempotent splitting, where idempotent means some operator E that satisfies the equation E squared equals E. And this actually creates a splitting of the space into an image and a kernel. And in logic, we have the distinction between true and false, and in form, inside and outside. And here the unifying idea, every system begins with a boundary-making act. And the primal act of telling apart is the phenomenological version of this formal law. And here, I would like to now consider the transition from mind how our mind behaves in the case of Rubin vase to how we work with symbols or to symbols. Now, Alexander Borovic in Mathematics Under the Microscope and in other works suggests that math lives in a human brain with a very specific hardware, and certain mathematical faculties are in some sense hardwired into the functioning of our brain and of our perception. And normally counting is associated with a process that is temporal, that takes place in time. But we also can recognize certain shapes of numbers instantly, and this is called subitizing. So, for example, consider the dots on the surface of a dice, of a dowse. Immediately from the shape of the dots, we recognize what number it is. And we have mirror neurons that feel symmetry and transformation. And in mental imagery, we see and manipulate abstract objects. And the act of focusing mentally on part of a diagram is a cognitive idempotent. And then we then externalize this with tools, pen, paper, and notation. And Mathematics Under the Microscope reminds us that abstraction is built on a biological foundation, and the formal idempotent we'll see is the crystalline form of this mental focusing gesture. So here, as I mentioned before, for example, if V is a vector space and E is a linear transformation, and if E satisfies the equation E squared equals E, or E composition E equals E, we call it an idempotent. And the idea is you transform the space once, and then you're done. If you try to transform it again, there is no longer any change. So this is, once is enough kind of a situation. And here, the whole space can now split into the image of E and the kernel of E, where image of E consists of the elements E of V, as small v ranges over the vectors in the vector space, and the kernel contains the elements V minus EV, the remaining part. And this is reminiscent of the part that we focus and the part that we ignore or we see as the background. So it's a splitting. And here E is a projector. It picks out a subspace, the image, and annihilates its complement, the kernel. And this is abstraction of focusing. And the map E is a rule that says, keep this, ignore that. It's a formal splitter. Now, I would like to take you through a small mental exercise, something that is not terribly complicated. That's about weakening the axioms of a vector space. And I want to bring this out because it reveals us a structure about these idempotents in some sense. Normally, scalar multiplication is very strict. 1 times a vector, with the scalar 1 times a vector, is equal to the vector itself. In other words, scalar multiplication by 1 acts as the identity transformation. Now let's relax this condition. Suppose we have a ring map from the, let's say if it's a real vector space, from the field, from the scalar field R to the endomorphisms of V, where endomorphism means linear transformations from V to V. And let's not demand that the map, the image of 1 is the identity transformation. Then rho 1 is just an idempotent E. And we will see in a second why. That the ring, the algebraic conditions, the ring conditions sort of enforce this. The axiom 1 times V equals V forces the splitter to be identity, no focus, and everything is preserved. Weakening lets a non-trivial splitter appear, and the space is not a simple vector space anymore. It's a direct sum of a module and something else. And this is a profound lesson because by relaxing a rigid rule, we uncover a hidden decomposition and the structure becomes richer, and this pattern repeats everywhere. Now, vector space axioms in standard form include this condition. And this can be weakened under certain conditions. We're going to explore two theorems. Let's say scalar multiplication is twisted by a fixed scalar alpha. And secondly, let's say we have an operation denoted by this circle, where one circle V equals V can be derived from distributivity and a mild non-degeneracy condition. So the first theorem is let V be a vector space over a field, and this black dot denotes scalar multiplication. And now define lambda circle, open circle V, as lambda times alpha times V. So it's the twisting factor alpha comes in, where alpha is a scalar from the field, lambda is a scalar, and V is a vector. Now, suppose we iterate this. So suppose two scalars, xi and eta, successively act. And suppose this, as in the definition of a scalar multiplication, we have a rule that looks like associativity, but maybe more properly a rule that should be called compatibility of scalar multiplication, twisted scalar multiplication with field multiplication. If we have this equation true, then the twisting factor alpha can only be 0 or 1. And the proof is, very straightforward. It's just basically using the definition of the open circle, introducing the factors alpha, using the compatibility of scalar multiplication with a field multiplication to shift the parentheses, and then using the commutativity and associativity of multiplication in the field to bring out the factor alpha squared. This is on one side. And on the other side, if we do the evaluation, this time only a factor alpha appears as opposed to alpha squared here. So then, because this is true for all possible scalars xi and eta and all vectors v, then there exists a non-zero V such that this holds. So then the only way this is possible is if the scalars are in fact actually equal to each other. And this gives us the equation alpha squared equals alpha, which in the field has only the solutions 0 and 1. And this sort of scalar equation is reminiscent of the definition of an idempotent. Now, again, now, the other theorem is, suppose we have an abelian group V with a 0 element and an additive inverse, and this is an abelian group, and F is a field. And suppose we have a circle operation from field times V into V, satisfying these three conditions, and we're going to assume, instead of the strict condition 1 times V equals V, that one circle U being equal to 0 implies that U is 0. In other words, the kernel of the operation of operating by the scalar 1 on the vector space is trivial. If this is the case, then it has to be the case that one circle V equals V. So that condition, that axiom is actually no longer could be weakened not to be an axiom. We could replace this axiom instead, and it follows from this condition and the other assumptions that which was once an axiom actually holds as a conclusion. And again, the theorem is simple. The proof is a simple computation. So we want to actually understand how one circle V and V differ from each other. So
what was the last condition? Excuse me, what was the last condition?
The last condition is that the kernel of operating by 1 through this circle operation is trivial. It has only the 0 vector as its kernel. One circle U equals 0 implies that U equals the 0 vector.
Okay.
That's the assumption. If that assumption holds, then it has to be the case that one circle V equals V. And these are the usual axioms. This SM1 is the compatibility of scalar multiplication with field multiplication, SM2 and SM3 are the usual distributivity laws. So then we look at the difference vector between one circle V and V. So how does this operation, one circle, differs from the identity transformation? Now let's just apply the one circle operation to U itself. Then, from SM3, in the first step, I just write U out, U from this expression, just substitute it there. And from the distributivity condition, I can distribute this one over. And from the compatibility of scalar multiplication with field multiplication, I can shift the parentheses in the first term. But 1 times 1 is 1, so then this is equal to 0. But then the assumption A1 prime implies that U has to equal 0. So one circle V has to equal V. So notice how A1 acts like a non-degeneracy condition. It says that the splitter, one circle, isn't completely collapsing. This is analogous to requiring that our attention mechanisms in AI don't completely ignore all inputs. The axiom one scalar product V equals V forces the identity splitter, and weakening it allows non-trivial projectors to emerge. And we can also see why A1 prime is necessary. Suppose we have the abelian group R squared under component-wise, coordinate-wise addition, and define the circle operation, lambda circle xy, lambda multiplying only the first component and the second component be collapsing to 0. In that case, we can check that the SM scalar multiplication conditions 1, 2, 3 are satisfied, but A1 prime fails because one circle 0, 1 goes to the 0 vector. If the first component is 0 and the second component is 1 or non-zero, it still goes to the 0 vector. So 0, comma 1, the vector 0, comma 1 is not the 0 vector, hence A1 prime fails. So the 3 distributivity axioms alone do not imply one circle V equals V, but the non-degeneracy condition is necessary and sufficient. And this pathological example shows that what happens without A1 prime. The splitter collapses the entire y-axis to 0, and in neural terms, this would be like attention head that completely ignores certain features that are useless for a learning task. And the non-degeneracy condition ensures the splitter preserves essential structure. And for example, the text Hoffman-Kunze standard vector space definition includes this as an axiom. Most texts will include this axiom and not, mention this minor point. But I did search online, and in fact, there is maybe a small article written about this topic that was written a while ago. But I basically discovered this while teaching linear algebra last year to students and puzzling whether this condition could be removed from the list of axioms of a vector space, whether that such would be possible or not. And it led to this result. Now, theorem 2 shows that this can be weakened. So distributivity and associativity and A1 prime is enough. And let's now go next to the question of how we measure obstructions. Obstruction theory in a nutshell is, the main question is, can we extend a structure from local to global? And here, of course, the terms local and global mean different things in different contexts. And in what I'm going to talk about, I'm going to mainly focus on algebraic geometry and maybe topology and the differential geometry and maybe differential equations kind of point of view about the transition from local to global. But of course, the terms also have a meaning in number theory or class field theory, where in localization refers to the process of focusing on a prime, which is kind of, in some sense, analogous to the geometric notion of localizing to a certain locale around a certain point. And whereas the global is looking at the big picture, let's say in number theory, the ideal class group or something like that. And obstruction is a cohomology class that measures the failure of how we cannot extend a structure from local to global. And the vanishing of the cohomology class, if the obstruction class is 0, then usually the answer is extension exists. And and a particular example of this is, when does a variety have a group structure? And this can be measured in an if and only if condition in a trivial obstruction in the second cohomology of the variety X with the sheaf coming from the tangent bundle. And now let's look at neural networks. The term local, we can think about it as task-specific performance, which is patches. And I want to think about the term global as multitask consistency, which is kind of like gluing, as in the definition of a sheaf. And obstruction is, in the context of neural networks or machine learning, I'm going to compare it to catastrophic forgetting, which is going to be the case if and only if there's a non-trivial, what I call a homotopy class, because the idea is transforming something kind of like, in a way, analogous to homotopy. And the solution is making architectural modifications to the learning process or algorithm to make the obstruction vanish. And here, maybe, we're not all familiar with the term catastrophic forgetting, but the way that I want you to sort of, I think about it is, for example, think of a juggler. If you are juggling only one ball, well, that's not too much of a problem. If you're juggling two balls, well, you only, one ball occupies one hand at a time. So again, that's doable. But once the third ball arrives in, the coordination task becomes suddenly more difficult. And that initially, if you are just accustomed to juggling one or two balls, when you begin to do the third ball, the new learning task or challenge destroys, you suddenly stop being able to juggle even two balls temporarily. So it's kind of like you have forgotten or you have missed what you already knew, because suddenly there is a higher demand of coordination or a new learning task that requires new set of skills. And this sort of, is relevant to actually machines learning. If you have, there is the notion of overtraining. So if you train a machine algorithm in a certain way to do a certain task, but you ignore certain aspect that is relevant to the question, suddenly when the new task arrives, the machine will blunder or not be able to produce the desired output. So that's kind of how I'm thinking about catastrophic forgetting. And the mathematical tools mentioned here are homotopy theory, which is continuous deformations between functions, and its application I'm thinking about as paths between network spaces. And maybe, so just sort of a, here, usually topology is, people usually make the analogy to, working with a coffee cup, right? So as you work with a coffee cup, or, things that are made of dough, you can play around with it and transform the shapes, and if things are identical, as long as there is no breaking apart. So the notion of a homotopy, most people are familiar, but there may be some that are not familiar. So in one end, you have a certain function when the parameter, let's say this parameter, think of it like time t. At t equals 0, you have a certain function. At t equals 1, you arrive at another function. And along the path, you sort of deform it. So one possible scenario is, let's say you have you consider paths connecting points A and B here. So if there is no hole in the middle, I will be able to deform this path, to these pieces, and start with a certain initial path and arrive at a certain final path. But if there is an actual obstruction, such as an actual hole here, even if it's just a single point, that hole is going to prevent me from deforming. I can deform this path up to here, but then I stop. I cannot pass to this one because of the obstruction created by the hole. So that's how homotopy theory enters to the picture in topology. But how does it relate to the network states? Well, by small changes in an algorithm or by the new information coming in, actually for example, in a neural network, it's usually we think about a neural network as kind of like maybe a graph, right, of certain nodes. So information comes in, signal comes in, and it arrives at these nodes, initial nodes. And then from these nodes, it goes to other nodes, right, to a second layer. And then from this other layers, and finally, all this information is collected in the neural network, and then you have an output. So that's kind of like a picture of a neural network. And what happens is there are weights that are assigned that control how the input is transformed to an output from one vertex of the graph to another. But these weights are adjusted. So, and in adjusting those weights, we're actually we can think about it as them being continually deformed as the network is learning something. So that's how I want to think about homotopy theory entering to the theory of neural networks. And sheaf theory. Sheaf theory is about data gluing consistently. And the application is neural activations across layers and model generalization as descent. And here, consistency, I want to give the example, for example, there is here a local global problem. For example, you have the problem of orientability, and we have the famous, let's say, Möbius strip, where we, twist this, right, and then glue. So, and such a shape, if I walk along it, if I try to put a vector field that's in one direction, a flow in one direction, so this is something, people play around with. So, so let's say we're twisting a piece of paper at the end and gluing these two ends together. That's how we get what is called the Möbius strip. Now, if I walk along this curve in the middle and the tangent vector is pointing in this direction, it comes out in the opposite direction. So if I want to actually create a consistent or global, sense of direction to the Möbius strip, it's impossible. That's why it's non-orientable, because when you twist around once, suddenly the arrow is pointing in the wrong direction, and in the second tour, it will contradict itself. It will reach a contradiction, which is an obstruction to globalizability. And similarly for the Klein bottom. And that we can think about as, the idea of a data gluing consistently. So choosing a sense of direction, a frame in a manifold or something locally, is the local data. Now, that the transition maps have positive determinant is a consistency condition of being able to glue things properly so that you have a consistent picture. And there is the famous example, of course, from topology of the hairy ball. Can you, so the idea is the hairy ball theorem. So if you wanted to comb your hair in a way so that there are no bald spots, it's impossible to do on a sphere. You will always get these bald spots. And by combing, I mean, it's essentially choosing a consistent direction in the tangent plane at each point on the sphere or on the geometric object. But when there is a hole, as in a donut, such a consistent choice can be done. And all this is, this can be measured through cohomology groups. So although these notions are geometric or topological, we can switch to the algebraic side and capture these difficulties from the algebra. And where was it? Oh, there, okay. And in category theory, there is the notion of structure preserving maps. And, think about structure as something loose, right? Structure is anything you want to call a structure. It's basically a category. We think about it as we can picture it as a graph, where the nodes are the objects and the arrows, directed graph. Arrows are morphisms. Directed edges are the morphisms. And we allow multiple edges, etc. And we enforce loops at each point that correspond to the identity morphisms. And on top of the graph picture, we have the condition of associativity of composition. So, which probably everyone here knows already about associativity. So it's just the condition F composition G composition H being equal to F composition G composition H, which already holds for functions in the category of sets. So that condition is imposed on the graph picture. And this, the application of the category theory is neural symbolic adjunction, which I'll explain shortly. And this is formalizing the integration problem. And obstruction theory has cohomological measurements. As an application, we already mentioned, this is about, the question, when is a variety, when does a variety have a group structure on it? When can a variety have a group structure? And in potential use of obstruction theory in this context is quantifying the learning difficulties. Okay, this is already something I already talked about, so I'm skipping it. And I want to get to quickly to motives. In algebraic study, we study varieties, which are solutions to polynomial equations, zeros of a polynomial of multiple variables, to say very succinctly and shortly. And a motive is a hypothetical universal cohomology theory piece. How do we get these pieces? Via projectors or idempotents in what is called the category of correspondences. And correspondences here are the morphisms of the category of motives, maybe hypothetical category, I should say, but we still have a category. It's just we wanted to satisfy certain properties, and certain properties have conjectural relations to the what are called standard conjectures in of Grothendieck. And here the idea of idempotents, this is kind of like finding the building blocks of a variety. And how do we do that? Well, in the sense of a, since these are multidimensional objects, and the relation between a dimension and a higher dimension is crucial to understanding the whole picture. So with a variety, we cut it with hyperplanes. So if this is a surface, we cut it with ordinary two-dimensional planes, and the intersections are curves, and we study how those curves deform over the surface. So we find the building blocks of the whole surface from the one-dimensional objects, which I'm sure happens a lot in three-dimensional geometry and topology, or others, studying how you can decompose a surface into maybe as built from knots or deformations of knots or one-dimensional manifolds, submanifolds. So the projectors idempotents are basically, as in the linear picture, they split a space into the kernel and the image of the idempotent. And here we want to think of it as splitting a variety into a motive, x comma p, where p is an idempotent that satisfies this relation. And projector is a formal way to say I only care about the cohomological aspect. It's an algebraic scapel. And the variety is like this twisted object, rich, continuous, and hard to study all at once. And projectors act like conceptual cutting planes separating geometry into pieces that can be analyzed independently. And from splitting to symmetry, there is the arithmetization problem. We've split varieties into motives. When is a variety itself group-like? In other words, when can I give it a group structure? Basically, a group, for those who may not know it or who may not remember it, a group is basically a set with a single operation on it that has an identity, that it has an inverse, and the group operation is associative. So associativity, I already mentioned, shifting of parentheses. So that's what a group is. So of course, the real set of real numbers under addition is a group. Of course, it's in fact an abelian group, because on top of it, the group operation is commutative. But if we have an arbitrary curve, it's not intuitively clear at all why it should acquire an arithmetic structure. And there is the beautiful example. Elliptic curves are, in fact, group varieties, and the group operation is defined actually geometrically. So we take 2 points on an elliptic curve, we consider the line through them. Since an elliptic curve basically, again, it satisfies, in general, an equation of the type y squared equals x cubed plus ax plus b. I mean, maybe there is a second order term, but we can assume without loss of generality that there is no second order term. So it is of this form. Now, if I restrict this equation to a linear, relation of the type ax plus by equals, I should add cx plus dy equals e, where c, d, e are scalars, a and b are scalars fixed, and y and x are the variables. If I look at this system of equations, then obviously this turns into a single, I can reduce the number of variables from the second equation, and then I end up with just a cubic in one variable. And such a thing has obviously 3 roots when roots are counted with multiplicity, and that gives the addition of the points p and q are defined through the last remaining point that this line passes through. And in case this is a tangency, then because of the double root condition, minus r is defined as the same point. So if you had q and then a tangent line going here, P here, minus R would be P again, because that's a double root. And then we also now reflect this and find the addition, define the addition on the elliptic curve through this rule. And it turns out that this is an abelian group. And but not every variety can be a group, and there is an obstruction to this. And classical obstruction theory is says that the whether a variety has an abelian group structure, it lives in certain cohomology groups. And the rigidity principle says, imposing a group structure is something very rigid. If it exists, suddenly the group operation has to be commutative, and the group law is uniquely determined by the identity point. So the tangent space at identity becomes a Lie algebra, well, what is known as a Lie algebra. Now, the concrete measurement, the first obstruction lives in the zeroth cohomology of the variety with the sheaf coming from the tangent bundle. So this is basically global vector fields. It's a globalizability condition. And again, the zeroth cohomology class, the zeroth cohomology vector space must have the same dimension as the dimension of X. So that's the first obstruction. If this condition holds, then it's impossible to have a group structure. And then there is higher obstructions, which are related to deformation theory, that have to do with the higher cohomology groups. And the abelian variety case, it requires what is called a polarization in algebraic geometry, ample line bundle with certain technical properties that I won't get into. And again, there is an algebraic structure called the Néron-Severi group that measures this, all this. And again, I'm not going to delve into the technical details because I want to fit everything in. So I want to get to from geometric obstructions to learning obstructions. So in algebraic geometry, we had the question when a variety wants to be a group. In machine learning, network wants to learn both tasks A and B. The obstruction lives in cohomology. Obstruction to having both tasks accomplishable in the same model. It's kind of like, having the same algorithm. You could have code or an algorithm that performs a certain task, a certain function, if you will, and then another function doing some other task. Now you want to basically merge these functions or algorithms to one algorithm that can do both tasks together. And that isn't simply, just adding or concatenating them, but doing this in such a way that maybe you even have a whole spectrum of tasks that are accomplishable between A and B through the more general algorithm. And this is measured by the specific cohomology groups in algebraic topology side. And I don't yet really know what it would be measured by in machine learning. And I want to guess at this moment, I'm still exploring these possibilities, what's called loss landscape curvature or task interference, where, requirements of a certain task interfere with requirements of another. In algebraic geometry side, the solution is adding a structure called polarization, or realizing that it's impossible to add such a structure. And in machine learning, we also add some structure to our algorithms. There is, usually in machine learning, it's based a lot on statistics, but the field changed through the article called "All You Need Is Attention," and attention. The idea of attention and residuals came to the picture, and that gives some structure to machine learning. And the philosophical parallel, both are about when a space, variety network space, can support a desired algebraic structure, group law, or consistent multitask learning. And here's a beautiful parallel. In our neural networks, we have a state space that we want to support a certain structure, ability to perform multiple tasks consistently without interference. Catastrophic forgetting we see is an obstruction to this. Just as cohomology groups measure obstruction to arithmetization, we might imagine homotopical or cohomological invariance of networks' loss landscape that measure the obstruction to multitask learning. And architectural tools we add, like attention mechanisms, are adding a polarization to an abelian variety. They provide extra structure that helps overcome the obstruction. And now I want to shift to a little bit to knot theory and try to mention how idempotents appear in knot theory as algebraic filters. And there is the temporally Lieb algebra that corresponds to basically algebraic structure in order to classify knots, understand knots or braid groups, etc. Or strands, and we have the algebra of n strands with certain algebraic relations given by these two. And this models planar knot diagrams up to Reidemeister moves 2 and 3, and the constant delta is a loop value. It's a quantum parameter. And here diagrams are algebra, and generators EI are natural splitters. So they are kind of like idempotents. They cap off adjacent strands, isolating a pair from the rest. But they are not quite projectors yet because they satisfy the equation EI squared equals delta times EI.
Excuse me, have you ever heard of obstructions which would be picture valued? I mean, possibly we can make a distinction between the classical world and the virtual world, between what can be drawn on the paper and what cannot be drawn on the paper, between invariants which are just numbers for classicals and which are pictures for virtuals. I'm interested in whether this also fits into your topic, because we had some works with Luke Kaufman on picture-valued invariants, and I have a whole book on that called Invariants and Pictures. And in some sense, there are projectors. One can project classical virtual knot theory to classical knot theory, and also one can project virtual braids to classical braids.
That's a very, very interesting question that I think would be worth exploring. I cannot immediately give a definite answer, but it's definitely worth looking into. And that's sort of, my hope in some sense. So, I mean, this is maybe also what it reminds me in the machine learning side is, or in learning, even for human beings or societies, usually, we teach, or even let's just consider mathematics pedagogy. We teach people, all solved problems, but we expect mathematicians to solve unsolved problems, or to be able to at least attack or make some improvement on unsolved problems. So this whole notion of, what cannot be drawn on the diagram is kind of like, what is not known yet, what is not yet discovered. And I think that would be a sort of interesting parallel, and I would definitely be interested in looking further into the details of the correspondence between virtual and classical worlds. Thank you.
Yes, and in some sense, my dream is that all problems, all obstructions are planarity abstractions. So good objects are planar, and bad ones are not bad, or complicated are non-planar. And there are projections from one objects, for example, from pictures on surfaces to pictures on the plane, and from virtual knot theory to classical knot theory.
I mean, the analog in the theory of motives, I didn't get into the details, is to do with, we think of the cohomology theory in some sense linearizing a motive. I mean, in general, the polynomial equations, these are highly nonlinear objects, but we look at cross-sections with hyperplanes, which is kind of like a linearizing or focus, and that's kind of like looking at how it is split in the cohomology theory side. And that's, you know, looking into invariance in algebraic geometry, I think. So that could also be potentially an analogous question in the other field, and just as interesting just to delve into in terms of knot theory and topology and even quantum field theory, I should say. But I'm not sure if, you know, everything can be planarized or linearized. I think that, you know, and even if it could be, you know, you're thinking in terms of pictures. When we speak about linearization, I'm thinking about the algebraic aspect of it too. Even if we were to just focus on studying linear transformations in vector spaces, the algebraic invariance to do with uh, linear transformations are things like determinants and eigenvalues. Now, that's a very nonlinear thing. That's kind of like, in order to study something linear or classify linearity, you still need to detour into nonlinearity. So, but again, I'm not saying this really addresses your initial question. I just wanted to bring out another viewpoint, but maybe for knots, I mean, the thing is, after all, in classifying knots, we always want to think about them in terms of the knot diagrams. So yes, I mean, I agree with the perspective that we should be able to, you know, most of the time do it through through the projections to a plane.
Okay, so please go on.
Okay, now Jones-Vance projectors act as universal filters, and this is a special idempotent called P sub n in the temporally Lieb algebra n with the parameter delta. So we want to find such a true projector, Pn squared equals Pn, such that it kills all the lower terms Ei, and whether such a thing could be universal, defined for generic delta and no further choice. And there is apparently in the literature a recursive construction of it, and I'm not, you know, I'm trying to get familiar with the technical details here myself, but this is sort of what I found out about it so far. So you have this recursive construction, and you have the Q parameter quantum integers, and the crucial point is Pn exists when the quantum integer is non-zero for a generic Q, and then there is a unique idempotent that satisfies the condition we want of killing off the lower order terms. And Jones-Vance projector is a filter. When you apply it to any diagram, it annihilates any term where cap EI appears, and it isolates components where all n strands go straight through. It's the algebraic embodiment of focus only on the highest weight component. And there is sort of a algebraic background to all this in relation to quantum groups and in relation to temporally Lie algebras. So here, the Lie algebra SL2 has the classical symmetry with the conditions where E, F, H are the generators, and the quantum deformation Q is basically defined through such equations, where here K, the new symbol K, is the parameter q raised to the exponent h given by this matrix, which I guess resembles the the condition in knot theory, right? Usually you have the q inverse terms in smoothing of a knot in the Jones polynomial. So all this material is related to that, and this is how it basically is. And here H is the 2x2 matrix with 1 and -1 along the diagonal, and then these equations are satisfied in terms of the generators and the commutators. And why does this matter for knots? This has an R matrix, braiding relations, representations label knot invariants, and temporal leap is a quotient of UQ acting on the strands, and Jones-Wenzl PN projection are the projections onto the highest weight subspace. So this is kind of like when you have just loops or just strands that are vertical, kind of like ignoring them is I guess the analog of it. And the categorical view in the category of tangles applying Pn to n strands yields an ideal splitting of the temporally Leib algebra to Cpn and direct sum with the lower terms. And lower terms are killed by Pn. So this is reminiscent of the initial point of the talk with projectors and idempotents. Okay, and then there is the relation of this to topological quantum field theory, construction within Reshetkin and Turaev invariants, and anion models in quantum mechanics, non-abelian anions corresponding to projectors on braid groups. So then this whole very theoretical thing has an actual physical counterpart in some sense. And this is also related to topological quantum computing, where quantum gates are realized by braiding strands whose ends are capped by these projectors. So I'm going to rush very quickly so that I don't overgo in time. There is the topos-theoretic view. Belfiore and Bennequin they are actually trying to create the theoretical background for machine learning and deep learning in particular. And they use topos theory and sheaves and the notion of fibrant states in order to be able to accomplish this. And a topos is a mathematical universe for variable sets. A neural network can be seen as a sheaf with data across layers and patches that must agree locally. And a fibrant state is a robust, globally consistent configuration, and learning is a homotopical process of deforming the network state to become fibrant. And this is a powerful shift in perspective. Network isn't just a function, it's a space of possible states, and good states are those that are coherent everywhere. And pathologies as homotopical obstructions, again, as I mentioned before, let's say, learning task A corresponds to finding what I call a fibrant state SA, and learning task B on top of task A means finding a new state S, A, and B. And the obstruction is whether there is a continuous path homotopy from SA to SA state SA and state S, A, and B. And this is kind of the picture for it. And the generalization gap, training well on patches is kind of like having local sections, and a failure to glue to a global section on unseen data. And this becomes a descent problem. Local consistency does not imply global consistency. And here maybe architectural splitters may come to the rescue. Residual connections where the output is, created by using both the input and a certain, action on the input, a certain transformation on the input, added, combined together. Or, we can replace, of course, addition with subtraction. We can look at the difference between the input and the output just as well by, switching our point of view with f of x to minus f of x instead. And here, each layer makes a small perturbation of the identity, and this corresponds to easier to find homotopies or smooth paths during training and promoting stable incremental refinement. Normalization layers, batch norm or layer norm, act as condition-dependent stabilizers. They project activations onto a nice subspace, zero mean unit variance, reducing internal covariate shift. And these aren't just engineering tricks, they are learned conditional splitters that shape the network state space to be more navigable or more vibrant. And this is sort of the small picture to illustrate it. So you have the input coming in, splitting to the coming out just as itself versus it being transformed through a learned transformation, and then this is combined to give the output. And explicit rule-based splitters coming from logic. Now, usually, machine learning and machine learning is based on statistical or laws, right? It's closer to being something empirical as opposed to something theoretically and deductively based. And as a result, usually in order to be able to have a machine learning algorithm accomplish its goal, you need, massive amounts of, energy and massive amounts of training and learning with input data and reinforcement through expecting a certain outcome or rewarding the system for producing outcomes that are closer to the desired ones. So, this is how, let's say, the simplest example of, identifying a picture of a dog as a picture of a dog versus a picture of a cat as a picture of a cat works. But now the question is, can we introduce logic or formal systems to for controlled splitting? Modest ponens, given A implies P and A, split away worlds where B is false. Neurosymbolic AI, the grand challenge is marry neural pattern recognition, conditional idempotents with logical rigor, and introduce logic as a constraint enforcer and project neural network outputs onto the subspace of consistent, deducible answers. And this is where splitting becomes conscious and verifiable, and AI doesn't just have a feeling, it has a proof. This could solve hallucination and trust issues. And I mentioned before that we want to think about it, through the adjunction mechanism in category theory. So you have let's say, the forgetful functor U going from a symbolic system to a neural system, and you have the adjunction functor going from, the free functor going from the neural system to the symbolic system. And Vasily, maybe we can analogously think in relation to your question, these functors, going from the virtual to the classical, or going from, the actual knots or surfaces embedded in some, higher dimensional Euclidean space, and their projections to planes or their diagrams. We can think about maybe these two worlds. where the diagrams become the symbolic system and the neural system is the actual thing we want to model. So, and then the adjunction, what is called adjunction, is basically in category theory a natural transformation between the identity transformation and the compositions of these two functors. So we can form two compositions. There's the composition, first apply F, go from the neural system to the symbolic, and back, forgetting the symbolic, back to the neural system. So that should be deformable to the identity transformation in the neural system. Or I'm using the word deformable, but maybe that's not precisely the right terminology. What is called in category theory as natural transformation from the identity to this composition. And then there is the other way. You start in the symbolic system, you go to the neural system, and you come back to the symbolic system. So I want to think about it like, we have some symbolic rules. We go and make observations in the real world, and those observations in return transform the symbolic system. So that sort of composition. So on the one hand, we have in the neural system maybe continuous pattern recognition. I want to say maybe continuous because in modeling, real world, for let's say differential equations, we usually assume that our variables are assuming continuous values in for example, as real numbers or complex numbers. But of course, quantum theory tells that the universe has a discretized nature, as in the energy levels of energy levels that could be occupied by an electron, or the solutions of the Schrödinger equation having certain discrete eigenstates. Or when we digitalize the system, analog to digital conversion, we're continually going to discrete world. And symbolic system is more closer to the discrete logical rules world. And I did put the word continuous there, but there is a question mark next to it in relation to the neural system, because how do we know whether a neural system is continuous? Well, because we want to think about the real world as continuous or smoothly, even smooth, there being no sudden jumps at all. But the Hodgkin-Huxley model of a neuron, says that there is a sort of activation potential for a neuron to transmit a signal. But there is maybe a mixture of continuity and discreteness in the neural system. The integration problem, how to map continuous neural patterns to discrete symbolic rules and back. And the mathematical challenge is gluing the worlds. And the integration problem is factorization or descent problem. And neural net produces a rich, continuous, ambiguous, latent map, F, from the input to the latent. And the logic engine requires discrete, precise symbolic representations. And this, I want to remind you at the beginning of the talk, discretization is kind of like the distinction making, telling things apart, applying the transformation once. That is something, a discrete act. And the forgetting functor is how to map from continuous to discrete without losing the essential meaning. And possible mathematical formalizations, adjunctions, neural net as a free functor, logic as forgetful functor, training, finding units and co-units, and EM factorization, where this means the neural net generate the epi and the logic refine the mono. Epi, you can think about it, in set theory as epimorphism or surjective onto maps, and monomorphism, close to injections, embeddings, or one-to-one maps. And every map can be under certain conditions on what maps we look at, in Grothendieck's Tohoku seminar, there is this mention of how the epi-mono splitting of morphisms in general happen in an abstract setting in category theory. But this very abstract notion can maybe apply to neural nets. Um, and by thinking the details of what a one-to-oneness and onto-ness could mean in such a context. Because, learning is obviously about creating associations. For example, when I use the word chair, it refers to a whole, set of objects, and it has the potential to refer to objects that are not yet in existence in language. So how is the correspondence between the symbols we use and the the actual references of those symbols? Sheaves on sites, stalks and neural activations, sections over logical context equals kind of like proofs, and descent condition is maybe the notion of generalization in mathematics.
Maybe if we have epi and mono, we can expect to have something like index property. If we have a kernel and co-kernel, maybe we can get to some index theory.
When you say index theory, are you referring to like index of a global of a vector field, or
of Atiyah-Zinger? So we have an operator.
Oh, yeah. How do you connect it to epis and monos?
Well, I mean, homology starts when we have something epi, something mono, and what is left is homology.
Oh, right, yeah. The homology group being defined as a kernel quotiented out by the image, kernel of that's true. Yeah, that's a very good remark. Thank you again. And then sheaves on. I already mentioned this. So I'm continuing. If also, I mean that your remark also made me think about your earlier question regarding finding invariance. This whole quest for invariance is cohomology, and homology is an analog of finding invariance, and maybe in some sense discretizing in this sort of model.
Yeah.
Okay, so let me see how much. Okay, I'm more or less done. Some of these are, this is sort of like a recap of the whole talk. So what did I want to go over what we went through. So there is Merleau-Ponty's embodiedness, perceptual figure versus ground. We started with the vase picture, or the vase or two faces. And then we passed to the cognitive level of mental imagery and focus, also mentioned in Borovic. In fact, Borovic suggests strongly that we should study, for example, in mathematics learning, the difficulties that people have with learning certain concepts. Those could provide a very rich topic of investigation. The distinction between what is intuitively known and what is not so intuitive or counterintuitive. And he suggests or recommends, a marriage between cognitive science, psychology, and mathematics in his book Mathematics Under the Microscope, and that's why I mentioned the cognitive level. And also, neural networks or machine learning or machines themselves are modeled in some sense after the human brain, although, you know, not a complete replica of it, we're all the time, you know, delving into these deep questions of what is consciousness, what is thinking, will machines, you know, acquire general intelligence, intelligence at the level of a human being, and will they acquire consciousness? But we don't really know what consciousness is either. So it's a very difficult question. We then went into algebraic notion of symbols, idempotents, E squared equals E in pure math. And then we went to geometric aspects, architectural splitters in AI, attention and residuals, and the logical level of explicit rule-based reasoning. And here I would like to add, I didn't write it in the notes, but there is a researcher called Olivia Caramello who gave several talks, called, unifying bridges, how category theory works as a bridge between, different worlds, the same way, and how it's built out of algebraic topology, which people already are, most people are somewhat familiar with. But she also considers through topos theory the link between the geometric and the logical, which could be relevant in this context too. And here, each level is a new kind of splitter. It offers new power and new failure modes or homotopical obstructions. So there is a sort of recursiveness to this whole notion of this whole process that we're going through mentally in this very talk. Beyond computation, splitting and consciousness. Where does splitting happen? Does it happen in neurons, in microtubules, or in the universe? And is consciousness quantum gravitational computation? And Hameroff suggests microtubules might be working as quantum processors. Of course, these theories are, somewhat disputed, and there is a lot of neuroscientists who disagree with them. But there is, after all, such a theory, thinking that the human brain might have aspects that are similar to quantum processors. And there is the radical view that consciousness might be a fundamental property of the universe. And maybe in relation to this, I should mention that Conway co-authored a paper called if elementary particles, if we have free will, then so do elementary particles, in which, that statement itself was rigorously mathematically defined and proved. So that's also an interesting issue, Free will is the basis of legal systems, and we want to think of it as something, a property that is connected to consciousness too. And it's an interesting question whether consciousness is spread throughout the universe or it's only localized to this sort of conscious beings, live beings, with a neural system or with life. And if consciousness is about integrated information, tonony, or objective reduction, Penrose, then each moment of awareness is a global split of quantum possibilities. And the idempotent becomes cosmic. It's like collapsing of wave functions. And attention is biological harnessing of quantum selection. And that's sort of a badly drawn diagram, of what I just said. And here is the 5 levels that I mentioned before: embodied, cognitive, algebraic, geometric, and logical, and the progression. So this whole talk is an invitation to a conversation rather than, an actual, definite results reporting of definite results reached. And the central thesis is the structure of learning in brains, in mathematics, in machines can be understood as the progressive refinement of splitting operations from pre-reflective to formally verifiable. And can tools from pure mathematics help design better AI? And we talked about obstruction theory in relation to this, diagnosing, forgetting, and generalization failures ahead of time, homotopy colimits in designing architectures that compose tasks gracefully, and derivators and infinity categories, modeling the multi-scale modular dialogue between neural intuition and logical deduction. And the goal is not just more accurate AI, but more interpretable, composable, and aligned learning systems. And I have a whole bunch of references which probably need to be lengthened. And that's the end of my talk. So I would like to thank everyone for participating and being here and listening. And any questions?
So we enjoyed your talk. Are there any further questions? Well, possibly if someone wants to ask, there will be a lot of.
Yeah, I presume so. So basically, I mean, the slides have my contact information. So if we don't have time now, or if you want to ask later, you can obviously do that too.
Yeah, are really enjoyable, and we will really discuss a lot of things. So we sent you our book, and we will do more. We have a program reading books together, and we have a program logistic of thoughts. We have many programs, and thank you very much.
You're welcome. Which is logistics of thought?
Well, it has to be discussed separately.
Okay.
Thank you.
Thank you very much.
Bye.